Okay, so we finished talking about mass defect. Let's talk about binding energy. This concept is slightly more easier to think about because it has to do with something binding. Binding of what? Well, we're talking about nuclei. So the binding energy is the energy which is bound within the nucleus that binds the constituent parts together. And it's the energy equivalent to the mass defect. So there's two ways of thinking about it. Binding energy is either so the binding energy is either the energy required to completely pull apart the nucleons, or it's the energy released when the nucleus is formed from its nucleons. On the next slide, we're going to talk about the binding energy curve, because different nuclei have different binding energies. Some are easier to pull apart, some are harder to pull apart. And we also refer to the binding energy per nucleon in order to compare the different nuclei. We talk about binding energy per nucleon. However, before we do that, it's interesting to find out or to work out how much does 1 U of mass, 1 unified atomic unit of mass, how much is that equal to in energy in joules? So from E equals mc squared, if we put in a mass of 1 U, which is 1.6605402 times 10 to the minus 27 joules, times the speed of light. Now they use a very accurate value for the speed of light here. Normally I just use 3.0 times 10 to the 8. Here they've used a more accurate value, 2.9979 times 10 to the 8. And then we have to square that number. All of that will be in joules. Do the maths, you get it out something equal to 1.4923946 times 10 to the minus 10 joules. Now that doesn't sound like a lot of energy, but on the atomic scale, it's a lot of energy. If we convert this into electron volts, and how did we convert into electron volts? How do we convert joules into electron volts? Ivan, you told me that last time. How to convert a joule into electron volt? Divide by the charge on the electron. So we divide by charge on the electron, 1.60217. Again, they've used a very accurate value. We get out a value which is in the order of mega electron volts. and there's a value here, 931.5 MeV, mega electron volts. So one tiny little unified atomic unit of mass is equivalent to 931.5 mega electron volts. Yep.
What are you dividing by?
This is the charge on an electron.
Yeah, yeah. And then what with the one above it is you're dividing
Joules.
Yeah, joules.
To get from joules to electron volts, we divide by the charge on one electron. So basically, very small changes in mass, because the unified atomic unit of mass is very small mass, gives me a lot of energy, because we multiply it by the square of the speed of light. People realized the possibilities from this equation, the fact that energy was equivalent to mass times by the speed of light squared. When they realized that, then they started working on it like crazy. Yeah?
The 10 to negative 19, what unit is that? Coulombs?
Yeah. Right, so here comes what's called the binding energy curve. And you have to know its properties. Basically, it tells you the properties or the binding energies of all the nuclei that exist. So we have on this side we have binding energy per nucleon and the units here are mega electron volts. On the bottom here we have nucleon number A. It's a bit less accurate what they actually require of you to know of this binding energy curve on the new syllabus. In the old syllabus, you'd have been required to annotate it. So we start off with hydrogen 1 down here. It has a binding energy of 0 because we can't, it's just a proton, we can't pull apart just a proton, okay? It's just down there, so it has 0 binding energy. We can't pull it apart any further. It's just a proton. Well, obviously then we can bash it and make it into other more exotic things, but that's not what binding energy is. Then there's a sharp rise. Yeah, it goes up like this. We have a peak somewhere around 7 mega electron volts per nucleon. It goes up to helium-4 is rather stable. Then it goes down again before going up again and peaking again. It's kind of curves up. You don't have to know the in-between bits. Peaks again for carbon. Carbon-12 is surprisingly stable. And oxygen-16 is quite stable. That's why we find lots of that in nature. Carbon and oxygen. And then it curves up, goes down again, and it curves up. Actually, the most stable nucleus in nature is, or the peak is at nickel 62. And then it kind of curves slightly, tails down here. And right at the end you've got, for example, uranium 238. Iron is also up here, it's quite stable, iron 56. So we have a sharp rise on the at low nuclear numbers, and then we have a gradual, a gentle drop after nickel. And most common values of binding energies are between 7 and 9 mega electron volts per nucleon. So if we're talking about nuclear reactions, which we're going to do in the next slide, then on the left-hand side of nickel, you tend to be able to, or in order to, because the further up you go on this curve here, the more stable nuclei you're getting. So on this side of the curve, if you want, or to make things more stable, they would tend to, or you would tend to make things more stable by fusing them together. This is what happens in stars, what we're trying to create here on Earth in fusion reactors, but not got very far. In order to get more stability here, nuclei have to undergo fission. Have you heard of fission and fusion before? Yeah. So this is the binding energy curve. Get to know its properties, the ones I've just mentioned, okay? Now, next we're going to talk about energy released in a decay. Not when we putting the constituent parts of a nucleus together, but when we go from one type of nucleus to completely other type of nucleus. Basically, we have, let's have an example. We have the decay of radium. This is one decay. Radium-226 with 88 protons decays to radon-222 plus an alpha particle. Now, if you work out these are called the reactants. People in chemistry will be familiar with that terminology. Mass of reactants. And this is, we can work out the mass of the products. Then if we, the mass difference, delta M, mass difference, is equal to the total mass of products minus total mass of reactants. And if the mass difference is positive, energy is released. If the mass is negative, then we need to supply energy. For this thing to happen. Yeah? Yeah, you're right. Thank you. Mass difference, total mass of reactants minus total mass of the products. If the mass difference is positive, energy is released. If mass difference is negative, we need to supply energy. And that energy is often supplied in the form of kinetic energy by supplying a high energy, for example, neutron, or high energy alpha particle to begin with. So in this particular example, if you were to do the calculations, you get a mass difference of 0.0052 U. So is energy going to need to be supplied, or is energy going to be released in this example? Released. And how much energy is going to be released? What factor do I multiply this with to get it into energy? Okay. Yeah. There was another factor 2 slides ago. The equivalent of 1 U, 1 unified atomic unit in mega electron volts was? No, there was some factor. Multiplied by 931.5. So this is equivalent to 931.5 times that in mega electron volts, which is 4.84 mega electron volts. MeV. Just about squeezed it on there. Seems like I have some technical issues here when I'm saving the JPEG. Half of my thing disappears. Yeah. This line? 4.84 MeV. Oftentimes, students find these kind of calculations with mass difference quite easy. So all you have to do is you have to add up the left-hand side, add up the right-hand side, take the difference, multiply it by a number. Not too hard. So this is often an area which students do well on. Okay, I'll give you an example where we have to supply the system with energy. And this is when we do something called transmute nitrogen, or we do a transmutation of nitrogen. And this was first studied by a chap called Rutherford in 1909. Sounds like the stuff of science fiction, doesn't it? What we have is we have a nitrogen particle, 14 nucleons, 7 protons, and we bombard it with an alpha particle of high kinetic energy, and if we give it enough energy, it will transmute into an oxygen nucleus plus a proton. So if you work out the masses of these things, you get a mass of 18.005677, and if you work out the mass of these things, you get a mass of 18.006956. So if we look here, the right hand side is heavier than the left hand side. So this decay would not take place unless we gave enough energy to the alpha particle, equivalent to the energy that's missing. So this will only take place if alpha particle has sufficient Ke. And the other two types of nuclear reaction are, give me 2 minutes.
Yeah, sure.
Nuclear fission and nuclear fusion. This one is when we have a heavy nucleus decaying into lighter products, and this is when we have two or more lighter nuclei fusing to form a heavier product. Okay, and there's an example in the book. We'll have to go through those next time, but for example, just for the sake of completion, if we bombard a uranium-235 with a neutron, it has an immediate state of uranium-236, which then decays into barium-144 plus krypton, and then 3 neutrons. This is an example of a chain reaction because the 3 neutrons can then go on to start 3 more reactions and so on, if we have something called a critical mass. In this one reaction, energy, and often you talk about Q of energy, released in this is 173 mega electron volts. Loads of energy. And then fusion reactions, which we can't do on Earth at the moment, but that happen in stars. For example, you've got 2 hydrogens or deuteriums, they have one more proton. 2 deuteriums combining to form a helium-3, and 1 neutron. This, if you do the maths, gives us an energy, if we can multiply the mass difference with 931.5, of 3.26 mega electron volts, which is still quite a lot of energy and a possible useful source of energy in the future.